Hey AP Chemisters, this is Mrs. Vanderwall bringing you another edition of the Blankwalle series. Today we start with Chapter 14, Chemical Equilibrium. And this is actually a continuation from our kinetics chapter. There's a lot of similarities in these two chapters. So let's kind of see what we're going to be doing. It says, intro, up until now, we've assumed that the reactions will go to completion, as in the BCA table. Remember doing those. B stands for before, C was change, A was after. One of the reactants will be used up completely. We called it the limiting reactant. However, we're going to find out this won't always be the case. One of the reactants in a chemical equilibrium will actually still exist in the container. So the concept of a dynamic equilibrium, well, what comes to mind when we think of dynamic equilibrium? Well, what word just about jumps out at you is the word equal. So what's equal in a dynamic equilibrium? Let's find out. It's a condition in which the rate. Well, hang on a second. What is rate? Well, do you remember from chapter 13 what rate was? Rate was the change in concentration over the change in time. So it is a condition in which the change in concentration or the change in time of the forward reaction. Well, hang on. What's a forward reaction? You might want to write this down. It's where the reactants make the products. And so this change in concentration of the reactants making products is going to equal the rate of the reverse reaction. Well, what do you think a reverse reaction is going to be? It's where the products make the reactants. You might want to write that down. So overall, that the rate of the forward reaction equals the rate of the reverse reaction. So the rate at which the products are being made is the same as the rate at which the reactants are being made. That is a dynamic equilibrium. So let's kind of go down here and check out these pictures. Again, you want to write some stuff down here, but here we have a reversible reaction. So here is what we're talking about. We're taking H2 plus I2 to make 2HI. And if you can tell on your sheet, maybe not, that the kind of light gray is your H2, the little darker gray is the I2, and then the darkest is your 2HI. So as the beginning of time, the initial concentration, you've heard that before from last chapter, haven't you? So the initial concentration at time 0, if you were to count all these molecules, go ahead and count them. How many H2s do you have? How many I2s do you have? How many HIs do you have? Well, hopefully you find out you have 8 H2s, 8 I2s, and 0 HIs. So next, in the next frame, here we see 16 seconds have gone by, and what has happened? If you were to recount all your molecules again, you're going to notice you're going to have 6 H2s, and 6 I2s, and 4 HIs. And if you actually just set up a BCA table right now, you're going to see that that works out quite nicely. So then another 16 seconds go by. So we would expect that, again, our reactants, H2 and I2, would decrease, and our products, which is HI, would increase. And that is indeed the case. If you were to count your molecules again, you're going to notice you're going to have 4 H2s and 4 I2s. And now this time you're going to have 8 HIs. So the reaction is indeed proceeding as we would expect. So now what? Well, now we have, looks like 48 seconds have gone by. And we would expect maybe at this time, at the rate things are going, that all your reactants are going to be used up and you're going to have only HI left. Is that the case? Not at all. If you were to count once again, we have 4 H2s, we have 4 I2s, and we still have 8 HIs. These two did not change. Now, what do you think has really happened? Do you really think that perhaps, oh, they're all done reacting and these molecules are just kind of swimming around in their container and that's it? And the answer is probably no. So what might have happened? Well, take a look at these two guys down here. Perhaps those two product molecules had an effective collision where the orientation was right, and they had enough activation energy, and they collided, and guess what? They could have made more reactant molecules. And then maybe you could have had some reactant molecules like these two up here collide and form new products. So it isn't as though the reaction's done. It is, I mean, it's not done, but the concentrations have not changed. There are still effective collisions going on, whether they're reactant molecules or they're product molecules, but the net result is that the concentrations have not changed. So let's kind of look at what's going on in this thing. So I just kind of scroll down. And this graph is a picture of what's going on here. So at time 0, notice that we have the maximum amount of H2 and I2. And actually this blue and purple line should overlap, but you wouldn't see two lines if they did. But these are actually the same line because you have the same initial amount, 8 molecules. And notice we have 0 HIs at the beginning. Well, at 16 seconds later, at the second scenario, notice what happened. The amount of H2 and I2 have gone down, so there's 6 molecules, then the amount of HI has gone up, so there's 4 molecules. So it's probably somewhere around here is where letter B is. And then at letter C, it's probably someplace over here. Here we've had an increase in HI now of 8 HIs. Actually, it's going to be over here. I take that back. This is probably where letter C is. You have 8 molecules of HI, and you only have 4 molecules of the other 2. And then over here is letter D, where you have the same number of molecules. The concentration has not changed. So the delta concentration, or delta T, is the same if you're going here or if you're looking down here. They're both, in a sense, 0. So let's go ahead and turn the page. So 14.3 is called the equilibrium condition, and let's talk about what a dynamic equilibrium is. Dynamic means moving. So think of what thermodynamics means. Heat moving. Heat's being absorbed, heat's being released. You can have heat going from high temperature to low temperature. Heat moves. So what do you think a dynamic equilibrium is? Where things are still moving, but eventually they're at a constant rate. So dynamic equilibrium is where reactions continue to take place. The reactant molecules continue to be converted to products. Once again, I would write down right here, this is your forward reaction where reactants make products, and the products continue to be converted to a reactant. This is your reverse reaction. Forward and reverse reactions take place at the same rate at equilibrium. And also, how do you know if an equilibrium is or a reaction is at equilibrium or reversible? You see the double arrows. So what does static mean? Static means the opposite. It's not moving. So no reaction is taking place after a certain time. All product molecules remain products, just like in our BCA table. All unused reactant molecules remain unreacted. This usually occurs when you have a solid or a gas is formed. So now what? What are some examples of this reversible reaction? Well, I like to think of maybe like a terrarium. Don't you have evaporation occurring and condensation occurring? After a while, they occur at the same rate. That's why the plants don't die. Here's another yummy example of a dynamic equilibrium. It's if you want to make rock candy. So you make your rock candy, you heat up a supersaturated solution of sugar, you stick your string in there, and then you let the sugar form on that string. At that point, what happens if you were to cover that system? So put a lid on it. Is it done? Is it static? Is there no motion? The answer is no, actually, because you still have a dynamic equilibrium when you make your rock candy and then you cover the lid. What's happening? The rate of crystallization is the same as the rate of dissolving. So if you were to get out your electron tunneling microscope so you can look at the individual molecules of sugar, you would see that at the surface there is some being dissolved at the same rate as other sugar from the solution is going onto that sugar rock candy. So that is another yummy example of a dynamic equilibrium. So what's going on? How does this happen? What causes equilibrium? Well, at the beginning you only have reactant molecules, so what are they going to do? They're going to collide. Only the reactant molecules can collide to make some of your products. So in the middle, so as you are making some of your products, what can those product molecules do? They can go back and collide and make new reactant molecules. And so at equilibrium, this collision rate where the reactants collide to make products at the same rate that the products collide to make reactants. So that's at equilibrium. So why don't you go ahead and take a look at this graph here and go back and look at the one on page 1 and pause this as you come up with some differences. I come up with at least 2. Okay, hopefully you're back. The first main difference is notice your y-axis. This is reaction rate. What did graph on page 1 say? It said concentration. So that was an actual concentration value. That's how we counted up those molecules on page 1, and that would be your y-axis. But this one is not concentration, it's reaction rate. So notice that the forward reaction is fairly steep at the beginning because you only have reactant molecules. The reverse rate isn't as steep because you're starting to build up some of those product molecules before they start colliding. Eventually they start colliding and slow down because they're going back to make reactant molecules. But in the meantime, eventually what happens? That the rate of the forward reaction equals the rate of the reverse reaction, so that the lines actually are one on top of another because they're the exact same rate. So my two differences are the reaction rate is your y-axis here, and your two lines merge into one on this one. They don't necessarily have to merge on the other graph. So let's go ahead and see what's going on in the next page. Yes, the Haber process. Now, if you were German, you say Haber. If you were American, you'd say Haber. And anyway, Fritz Haber was a German around 1900. He was an up-and-coming young scientist, young chemist around 1900. And the big question was, would there be enough food to feed the rest of the world at this point? If you think about what's happening in 1900, the Industrial Revolution has really taken hold. More and more people have flocked to the cities. The population is just exploding. But there hasn't been many improvements in the farming techniques. They were worried that there wouldn't be enough crops available, that the farmers can't grow enough food for the growing population. So what could they do? Well, they needed a way to make better fertilizer at this point. And fertilizer is ammonia. If you look up here, this is your fertilizer. So what did Fritz Haber do? He found an inexpensive way to take the nitrogen from the atmosphere, from the air, react it with some hydrogen gas, which is fairly easy to make, and to make fertilizer. We're going to read about this or hear about this more later on in the end of this chapter when we talk about Le Chatelier. But in the meantime, just know that he's the one that created this process using the concepts of equilibrium to make the ammonia. Now, he is a very ironic character in history because it seems as though he saved the world. He found a way to make very cheap fertilizers so the farmers could make more and more crops to feed the growing population. As it turns out, the irony is, as he got famous from his Haber process, as he got very wealthy, he won a Nobel Prize, he caught the eye of the leaders of Germany. So he was actually the man in charge of the chemical warfare used in World War I, which was, the trench warfare. So he came up with the gas that they would throw at the other country. First time was on Britain, and killed a lot of men as they were, choking to death in their trench. Later on, his research was actually used for the concentration camps, the gas chamber. So here at 1900, he saved the world by feeding the people, and just a few years later, 20 years later, he was coming up with the science to kill a lot of people. So very interesting story, to me kind of tragic. But let's kind of look at this reaction here. We have N2 plus 3H2 making 2NH3. Notice right here, we're back to the same kind of graph as graph 1. We start with H2. Notice it's a slope is kind of steep. Why? Because its coefficient is a 3. And notice that nitrogen is only being consumed at a much lower rate. Why? Because its coefficient is only a 1. Hydrogen is consumed 3 times the rate of nitrogen. And here is ammonia being created in a kind of a medium pace here. Why? Because it's 2 times the rate at which nitrogen is consumed, because its coefficient is a 2. But notice at this dotted line, what happens to our graph? The lines are flatlined. What does that mean? Is there any change in concentration? No, there is no change in concentration. It's still a dynamic equilibrium because N2 and H2 are still colliding to make NH3, and NH3 is colliding with another NH3 to go back and form H2 and N2 again. But the overall concentrations have not changed. So that's the end of this segment. We would really appreciate it if you would go ahead and go on Schoology after this and look up this website and go ahead and fill out all problem number 2. See you tomorrow.